The last talk this afternoon is by Adam Harper about the Riemann zeta functions in short intervals.
Okay, so thank you very much, and thank you for the invitation to speak here. Very honored to be here. And I'm pleased to talk about what I think is a very beautiful subject. And I hope that by the end of the talk, some of you will think that also, at least as many people as think it at the beginning of the talk. So the plan is that first, I want to describe a couple of basic principles for thinking about the zeta function. And those of you who were in Emmanuel Kowalski's talk yesterday, some of this will be quite repetitive of things that he said. But despite that, I think that if you don't take anything else away from either of those talks except this is still something that's really worth knowing, that guides a lot of the kind of modern thinking about how the zeta function works. And then, so the title of the talk is The Riemann zeta function in short intervals. And in particular, I want to talk about a conjecture about the maximum in an interval of length, let's say 1, of mod zeta 1/2 plus IT plus IH. So an interval of length 1 on the critical line, the 1/2 line, starting at this imaginary part T. So this is a conjecture of Fyodorov and Keating. And also Fyodorov and Thierry and Keating. In 2 papers. So in the second part of the talk, I'll explain what the conjecture says, and a little bit about where it comes from. And then at the end, I'll say as much as I can about the proofs of some rigorous results in the direction of this conjecture. And this will be following two papers, both from the end of 2016. So one of Najnadol and the other of a team of people whose names are too long for me to write here, but of Argin, Bellius, Bourgard, Radziwill, and Sandarajan. So when I get to the end, I'll write out their names in full, and I'll say as much as I can about the proofs of the results. Right. So let me start by saying what the zeta function is. So when S is a complex number with real part strictly bigger than 1, then we define zeta of S by this absolutely convergent series, 1 over n to the S. And this definition can be extended analytically continued to the entire complex plane except for the point 1, where there's a simple pole. And in his talk yesterday, Emmanuel said a little bit about how you can do this, so I won't get more into that today. And the other fact that we'll need to know, which is due to Euler, is that besides this representation as a series, there's also a representation of the zeta function as a product over primes, the Euler product. So on this same range of S, we also have that zeta of S is the infinite product over all primes P of 1 minus 1 over P to the S to the minus 1. And this, so Emmanuel did this yesterday, but I can't resist saying why this is true. So this is just because this term that appears in the product here, this is the sum of a geometric series. So this is the sum over all k from 0 to infinity, 1 over p to the ks. And then if you plug this into the product, so the product over all p of these sums, well, you can get here any power that you want of every prime p raised to the power of s. And since numbers have unique prime factorizations, when you expand all this out, you get 1 over n to the s once for every term n. So this gives you the zeta function. Okay, so I won't say, as I said, much about how the analytic continuation of a zeta function is done, but the way it's done uses the series representation of a zeta function. It uses the fact that a sum over all natural numbers is quite a nice kind of smooth thing that you can work with. And in particular, the Euler product, which is very important, it's really one of the reasons why the zeta function is interesting at all, does not persist when the real part of s is less than 1. But an important thing that's going to guide our thinking is that although the Euler product isn't literally true anymore, still things like that should be going on. So for any s with real parts, bigger than or equal to a half, or maybe when the real part is strictly bigger than 1/2, the zeta function is still kind of like an Euler product. So we have that zeta of s is roughly like product over primes up to some length, which will depend on s. Or what would be the same thing. So if I multiply both sides by the inverse of this, so zeta of s times the product without the -1 here, this should be roughly 1. Right. So since I'm only claiming this with some inverted commas and some twiddles and things, then these statements are equally true or equally false when the real part of s is 1/2 or strictly bigger than 1/2. I'll say in just a minute why the 1/2 line is more delicate, more interesting. But certainly when the real part of s is strictly bigger than 1/2, you expect in a very strong sense that the zeta function should be behaving like an Euler product. And on the critical line, it's still true for suitable questions, and if you formulate it in suitable ways.
But when s is near 1, because of course.
Yes, okay. So let me say when the imaginary part of s is bigger than 1. Right. Now, why should we believe that something like this is true? Well, so if it's a finite product of things that don't vanish, then it can't be 0. So if this principle is true, then we should have that zeta of s is not 0. When the real part of s is, let's say, strictly bigger than 1/2. Now, we don't know how to prove that, because that's the Riemann hypothesis. But we can prove statements like, if you look at all s with real part bigger than 1/2 plus epsilon, for any fixed epsilon, then almost none of the zeros of a zeta function are in that region. So for any fixed almost none as a percentage, so asymptotically 0%. So that's known. Results like that are called zero density estimates. And the way they work is that you show that something like this holds for most s, with real part bigger than half plus epsilon. And if that's true, then zeta certainly can't vanish, because then the left-hand side would be 0, and 0 isn't close to 1. So this is supposed to be some kind of justification that this principle is not ridiculous. And we'll come back to other ways of kind of putting this principle into practice later on in the talk. Now I said that I'd say something about why the 1/2 line is different from the case where the real part is strictly bigger than 1/2. Okay, well, if I look at some quite general Dirichlet series, so A are just some numbers for the moment. And I look at this in a mean square sense as the imaginary part varies, then what I get is the mean square you can compute, so it comes out to be the sum of the squares of these coefficients. It's not absolutely obvious, but that's what happens if you do the computation. So now, if the ANs are sort of under control, if they're bounded in size, let's say, then if sigma is strictly bigger than 1/2, this is going to converge. So if, let's say, AN is at most 1, and sigma is strictly bigger than 1/2, this converges. So that means that the tails of the series are small, at least in a mean square sense, an average sense. Whereas if sigma is 1/2, and if the AN are usually about 1 in size, so if sigma is 1/2, this might diverge. Might not if they're all 0, but if they're an interesting kind of sequence, then it might diverge. And that means that the tails of the series have an important role in the behavior. And this is very important in things like the zero density argument, which I mentioned briefly up there. So in the product over primes, if you expand out the product, you get lots of terms, and you get lots of terms where the thing being raised to the power of s is very large. And these are difficult to control in the arguments. So if you're in a situation where, in some kind of average sense, the tails don't tend to be important, you can throw away these terms which are hard to control, and you can make the argument work. But if you're in a situation like on the critical line, where the tails really dominate the behavior, then you can't do that. And this isn't just a technical thing. We expect that zeros appear when you get to the 1/2 line. So we expect that, because of issues related to this, different phenomena start to manifest when you get to the 1/2 line. Maybe any questions about what I said so far? Okay. Right. Now, if you believe what I said, then the behavior of a zeta function is related to the behavior of the quantities p to the minus it, where p is prime, because they're the imaginary parts of the things in the product. So how are they going to behave? So the second idea here is that if I let my imaginary part vary over some interval, and here you should think of t as being, capital T as being large, and probably capital T will go to infinity at the end of the argument, then if I look at the sequence p to the minus it, which I can also write as e to the minus it log p, where p is prime, these will behave like in inverted commas again, independent random variables each one of them uniform on, so these have absolute value 1, so uniformly distributed on the unit circle in the complex plane. Now, the uniform distribution here I claim is pretty obvious, because for each one of these individually, as I let t vary, well, I'm just going round and round and round the circle at speed log p, or log p over 2 pi. And I'm going to cover every point on the circle essentially the same number of times, some massive number of times. So the uniform distribution is kind of okay. So the interesting thing here is the claim that we should think of them as being independent of one another. And this is because of uniqueness of prime factorization again. So y independent well, let's note that the sequence of log p's, these are linearly independent over the rationals, because if there was some linear dependence, you could exponentiate and you could move anything with a negative power over to the other side, and you get two different prime factorizations, some number, which is impossible. So there's no Q-linear relation between these things, so there's no kind of fixed relationship between the speeds in the exponential here. Now, this doesn't necessarily really mean that they behave like independent random variables, just because there's no kind of rigid fixed relationship between them. It might be that they interfere with one another in some other way. They see each other in some more subtle way as t varies. But we think that that doesn't happen, at least if the primes that you're looking at are sufficiently small compared with the capital T, where little t is varying. So I'll come on to that also later on. Right. So these are the two principles we're going to use to think about the zeta function. The zeta function is roughly like an order product, even quite far to the left in the complex plane where the order product doesn't converge. And the p to the minus it's, which live in the order product, are kind of like independent random variables, at least the small primes in the order product. Right, any questions up to here? Okay, so seeing none, I'll go on to the second part of the talk. So I want to think about large values of the zeta function. Now, if you're not so used to this subject, this might seem like a strange thing to be interested in because the zeros are the thing, right? But actually, this is a very classical problem. So I think I have a few minutes, so I'll give a very brief survey of some of the things that people are interested in with the large values, and then I'll go on to the conjecture of Fyodorov-Yerry-Keating. So how about upper bounds for this? Well, the best result is a result of Bourgain. So he proved that quite recently. So he proved that z to the half plus it is smaller than t to the power, I think, 13 over 84 plus epsilon. Yep. And this is true for any positive epsilon and all large t, but the constant here can depend on epsilon. So that's an upper bound. It's an old result whose origin we are currently investigating, that you can take 14 over 84 here. So in 80 odd years, there's been an improvement of 1 over 84 in this experiment. And lower bound, so again, there was a pretty recent breakthrough on this due to Bondarenko and Sipe. So they showed that if you look at the maximum, let's say between 0 and capital T of mod zeta, this is going to be bigger than something which is not as nice to write down as that, but something like exponential 1 plus theta log 1 square root log t log 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 t over log log t. All this horrible thing is in the exponential here. Little o1 means something that goes to 0 as capital T goes to infinity. And say as well, so this 1 plus theta log 1, this is being improved to root 2 plus theta log 1. This is by Lebretesh and Tenenbaum. And this is sort of the optimization of the Bondarenko-Sipe method. So this seems to be the best that can be obtained by direct work with this argument. Okay, so these quantities, I don't know how obvious it is, but this is a lot bigger than that. So where do we think the truth is here? So there's a conjecture about that. Of Armagonic Q's from 2007. So they conjecture that this maximum should be like the exp uh, 1 over root 2 plus the log 1 square root log t log log t. So this kind of looks like the thing that's in the Bondarenko-Sipe lower bound, but the function there goes to infinity faster than the function here. So that goes to infinity about log log t faster than this function here. Okay, so I'm just showing you these things to illustrate that this is really a problem that's attracted a lot of interest. These are all pretty recent results because there's been recent progress. But this is a problem that people have been thinking about for decades, certainly, going on 100 years. This is considered to be very hard. So there isn't absolute consensus whether the conjecture is even correct. And certainly we have no idea how to prove the conjecture.
And what's behind the conjecture? Just purely numerical evidence?
No. So one thing I'll say in a minute is that it's actually very difficult to investigate this numerically because it's difficult to find where on this big interval the maximum should be. So there is an argument from random matrix theory that supports this, and there's also an argument based on something like what's up there. That the zeta function is kind of like an Euler product, and the terms in the Euler product are kind of like independent random variables that supports this. Right, any other questions? Right, now, because this is so difficult, Fyodorov and Keating and Fyodorov-Hieri-Keating have proposed a different kind of maximum to study here, which is the maximum in a short interval. So this is Fyodorov Keating and also Fyodorov-Hieri-Keating. So they want to know the thing I wrote at the very start of the talk. So if I take the maximum in an interval of length 1. So now I have this t. So they want to know how does this behave as t varies up and down the line. And one of the reasons that this might be an interesting conjecture to think about is that this is subject to sensible numerical test, because you just pick a random point t, and then you look in this short window around the point t. So this is what they want to know, and they have a guess, a conjecture of what the answer is. From 2012. So let's suppose I have some real function g of t which tends to infinity, but at any rate you want. So maybe g of t goes to infinity very, very slowly. And then if I look at the proportion of little t, so 1 over capital T times the measure of little t in this interval, or the one from capital T up to twice capital T, doesn't make any difference. And they want to look at so the max, log mod zeta. So if I look at this, I subtract from it log t minus 3/4 log t. And I see how often this is less than my function g, which goes to infinity. Then this should go to 1, as capital T tends to infinity. This is the conjecture. So if this is a bit alarming, which it is, then all it's saying is that the maximum is about that size for almost all t. So for asymptotically 100% of t, up to an error given by your function g that's going to infinity, but at any rate you want, that should be true. If the log is alarming, well, that's the answer, so I can't do anything about that. Probably, because it is a conjecture. Right, now I want to make two remarks about how this compares with Farmer-Goniet Q's. Well, Farmer-Goniet Q's, which is still up there, is an extremal conjecture. It's asking about what happens for the worst point, the biggest point t. This is a distributional conjecture. So it's asking about what happens for most t, for 100% of t in the interval. So if you were in Emmanuel's talk yesterday, he talked about another distributional theorem, the Selberg central limit theorem, which is about what happens if you look at mod zeta at a single random point. This is looking at the maximum of zeta in an interval around a random point. So that's an extremal conjecture. This, so Fyodorov, Yerry, Keating, is a distributional one. And the other related thing is that if you look at the sizes that we're working with in these two conjectures, I've taken a log here. So for zeta itself, I'd have the exponential of this. So I'd have a log in the exponential. That's the size I'm interested in. In Farmer-Goniet Q's, I have a square root log in the exponential, roughly. So the size of things in Farmer-Goniet Q's is much, much bigger than in this conjecture. And that means that we're kind of much, much further into the tails of a distribution. We're looking at something that's going to happen very rarely. And that tends to be very difficult to control. Even in a probabilistic problem where there was no number theoretic issue, asking about very extreme tail events, very large deviations, is quite hard. Things that are in the bulk of a distribution closer to the mean are much easier. So Fyodorov, Yerry, Keating is about events closer to the bulk, closer to the mean. And this should give us hope that maybe Fyodorov, Yerry, Keating is more attackable than Farmer-Goniet Q's. And indeed, it's going to turn out that it is. Yes?
What is the status of the bound h between 0 and 1 if you replace it
Oh.
with h between 0 and 1/2?
This makes no difference. So any fixed interval non-zero would be the same. Okay. Now, Fyodorov-Hyary-Keating, they have an argument in favor of the conjecture which comes from statistical mechanics. So they have statistical mechanics or random matrix theory argument. It uses both. I'm not going to say much about that here. In the written piece that accompanies this talk, I say a bit more about that, except to say one thing, which is something I said in the abstract is that I tried to explain what this body of work, what these results tell us about the zeta function. Now, it's going to turn out that you can rigorously prove something like the Fyodorov-Hyary-Keating conjecture, not as precise, but something which is consistent with it. And it might be true, for all we know. But although the kind of motivation for this comes from random matrix theory, the proofs say nothing about random matrices. And this is generally true of work with the zeta function. So we can conjecture a lot of things by assuming that zeta behaves like the characteristic polynomial of a random matrix, a random unitary matrix. Some of them we can prove, but when we prove them, the proof never shows any kind of connection between zeta and something that looks like a random matrix, or characteristic polynomial of a random matrix. So that's not to say that such a connection doesn't exist, but these results, so far as they've been proved, don't substantiate that. They just show that the behavior is the same for some other reason. That's all I'll say about that. So what's another reason for believing the conjecture? Well, we can try to use things I told you at the start of the talk. So I want to know how this behaves. Well, principle 1 said that zeta is kind of like an order product of some suitable length. So if it is, and I can write anything here because I have a twiddles, so it's okay. So this is like the maximum log of the absolute value of a product of some length. And then if you remember what happens when you take the log of a complex number, log of the absolute value is the real part of a logarithm. So this is roughly the max of the real part. Then I have a product, so when I take the log, I get a sum. And then I'm taking the logs of these terms, and if I use the Taylor expansion, the dominant term is just this thing which is here. So I get one over p to the half plus it plus ih. And then I can use principle 2. So I'm interested in this as t varies. So as t varies, this should be roughly like the maximum where the f of p are the sequence of random variables which the p's and the it's are supposed to be like. So f of p are independent, and each one of them is uniform on the unit circle. Okay, so maybe you believe that might be true. Now, how is this maximum going to behave? So if we just look at a single point, so a single point h, and I'll just say h equals 0, doesn't make any difference. Well, it's a sum of a lot of independent random variables, none of them very large because of this normalization. So a sum of a lot of independent things should maybe be like a Gaussian because of the central limit theorem. So this is maybe roughly like a Gaussian random variable. The f of p is a symmetric in a distribution, so the mean is going to be 0. And what's the variance? Well, you can just compute. So because of the real part, you get a factor 1/2. And then you square all these things. So the sum over p less than x over p. And it's a well-known, this is a well-known number theoretic quantity. So this is roughly like a half log x, when x is large. And again, if you were in Emmanuel's talk yesterday, he did something exactly like this for the Selberg CLT. Right, but we don't just have a single point, we have this maximum here. So let's think about what happens at two different points. So so the dependence on h comes from the p to the I h in the sum. So if I look at p to the I h1, which is the same thing as e to the I h1 log p, this is going to be roughly the same as p to the I h2, provided that p isn't too big compared with the difference between h1 and h2. So this will be true when log p, which appears here, is smaller than 1 over h1 minus h2, or 1 over 100 h1 minus h2 if you want. And when p is bigger, then there's no particular reason for these things to be close together. So as h varies here, depending on how close together your two different points h are, some part of a sum, the part consisting of small primes, is going to look roughly the same at the two different values h. And the other part, there's no particular reason that should look the same at the 2 points. Another way of saying that, maybe for people with a more probabilistic background, would be that the correlation comes from the small primes, and the part on the large primes is discorrelated between the two sums. So you can figure out exactly what this means. So this means so every one of them individually is Gaussian distributed, and because of this, you get a logarithmic correlation at different values of h. Positive correlation structure and a particular form which involves some logarithms. And you can analyze this situation. So this can be analyzed. I'm not going to do it in the written piece. Again, there's some more discussion of how this works. And if you do it and you figure out how big the maximum should be, you get something that's consistent with the conjecture. Not as precise, probably just for inefficiency in the proofs. The answer should probably be exactly the same. But you can analyze the behavior to a certain level of precision, and it agrees with what Fyodorov, Fierro, Keating predict. So you get So this is another reason, maybe, for believing that the conjecture is correct. Right, that's the end of part 2. So any questions up to here? Yes?
So, you have this log T minus 3/4 triple log T.
Yes.
And for the corresponding random objects, I think on the final level you get something random.
So the log T minus 3/4 log T is the same. And then the big O1 term has some kind of distribution.
Yes, exactly.
Yeah, so I guess you'd expect, right, so you'd expect to see a difference on the scale of the big O1 term between this model and the actual zeta model. Yes?
Does this part explain the 3/4?
So the 3/4 is because you have this positive correlation rather than being independent at different points h. So if you did the analysis assuming that the points h which aren't really close, these things were just independent of one another, you get log T minus 1/4 log T. If you do it taking account of the correlation which actually exists, you get 3/4 instead. Other questions up to here?
Need to analyze 3 points or 4 points?
You only need 2 points because for a Gaussian random field, if you understand the correlations, you understand everything. Other questions?
So in a way, what is missing for having the full conjecture would be just to show that the actual Riemann zeta function is very close to the random.
Yes. So this is exactly what I'm now going to discuss. Thank you. Right. So I'll state a theorem. I'll just state a combined theorem for all of them, and then I'll say what they did. So this is a theorem of Ngajngadal and of Argand. And both of these, I'm sure he wouldn't mind me writing it like this. So both of these were on the archive in 2016. This one, I think, appeared in 2018, and this one appeared a few months ago. Right, so again, I'm going to have some function g of t, which goes to infinity at any speed that you want, provided it goes to infinity. And then, first of all, I have an upper bound. So if I look at the proportion of the legal t for which log, so max, log mod zeta is smaller than log t plus g of t. So how often does this happen? This goes to 1. As t tends to infinity.
G of T is positive?
Yes. Yeah, it tends to plus infinity. Right. Infinity is plus infinity for me. Right. And how about a lower bound? So also for any epsilon, if I see how often this is bigger than 1 minus epsilon log t, for any fixed epsilon, this also goes to 1. And this first thing, they both proved the same. And the second statement here, so Ngajnadol did this assuming that RH, the Riemann hypothesis, is true, and these other 5 people did it unconditionally. So if you compare this with the conjecture, it's not as precise. Neither the upper bound nor the lower bound see this 3/4 log term that should be there. But at the first order term, the log, it's correct. Right. So it turns out here that the upper bound is quite a lot easier than the lower bound, so I won't say anything about that. So in the last 5 plus a bit minutes, I'll say a tiny bit about how each of these 2 groups of people prove the lower bound in the statement. And in particular, I want to explain what was mentioned in the question, how you can show that the zeta function really behaves like the sum over primes, where you can do the analysis up there. So I'll start with this. So what he showed, assuming RH is something quite nice. So assuming RH for any large t, if you look at the maximum, let me say here, over mod h less than 1, although it doesn't make very much difference. So we want a lower bound for this. So he could lower bound this, roughly speaking, this isn't quite right, by the max over a slightly smaller interval. So let me say mod h less than 1/2. So a sum of the kind that we expect, and there's a parameter x in this sum, and you can choose x, but then there's an error term that depends on x. So the error term is something like log t divided by a big power of log x, plus also some big power of x over t. So you can't choose x to be t, otherwise the right-hand side will be far too big because of its error term. You can't choose x to be really small, otherwise this will be too big for it to be useful. But you have quite a lot of flexibility in choosing x, and in the end, so you choose x to be something like that, x of log t to the 1 minus epsilon. So you could also write this as this is t to the 1 over log t to the power epsilon. So this is t to an exponent that goes to 0 with t. This is why it becomes possible to do principle 2, the fact that the p to the minus it's are behaving independently for this range of primes, because the range of primes isn't too big. Right, so he proves this for a value of x where it's possible to compute power moments of these sums and show that they agree with the random model. Now, how does he do this? So I'll just say 2 things about it. So he needs RH, y. So this means that there are no So this probably won't make very much sense unless you are an analytic number theorist. But if you are, and you think of things like the explicit formula, the way you would classically link the zeta function to primes, if there are zeros of a zeta function off the critical line, these lead to big contributions in the explicit formula that we don't think should be there. So if you try to do this without assuming RH, and there were any zeros off the critical line, you get other terms on the right-hand side corresponding to the bad zeros, which shouldn't be there and which would spoil the argument. So RH is assumed to exclude the possibility that this can happen. And the other thing I want to say is that the maximum, so you take this maximum on the left-hand side, this is very important to making the argument work. So nothing like this could be true at a single point t, because you might just hit a zero of the zeta function, and then the left-hand side would be minus infinity, or something undefined, depending on your preference. But if you take the maximum, what he does in the proof is he replaces the maximum by a sort of slightly averaged version. That only makes it smaller. And the averaging lets you kill off the effect from the zeros. So because you're not fixed at one point, you can blur things about a little bit. You can get rid of the effect of the zeros. Okay, that's what I'll say about that. And how about the other people who do it unconditionally? So I guess the main thing that they exploit, the two main things, are first of all, it's okay to move off the critical line, the 1/2 line, a little bit. So it's possible in this problem to replace that by something that has even more terms inside the bracket. So by zeta of 1/2 plus w over log t plus it plus ih, where w is something that goes to infinity not too fast. So for example, with took w to be log t to the power epsilon, that's okay. This is because, well, the zeta function it's holomorphic, it's continuous, doesn't change too much when you only move by a little bit. So it's possible to show that if there's a large value of the zeta function a little bit to the right, the 1/2 line, there'll also be one close by on the 1/2 line. So they show this, it's not too difficult. And then, having got to there, so you exploit the fact that you've moved a little bit to the right, and also the fact that you only want something that holds for almost all t, not for every t. So Nash-Nadel's bound up there holds for every single t. You don't need that, because the result I'm trying to prove at the end is only a statistical one, as t varies. And if you exploit that, and you exploit the fact that you can shift to the right a little bit, you can prove something like that for almost all t unconditionally. This is the same kind of thing that we can't prove there are no zeros of a zeta function with real part bigger than 1/2 plus epsilon, but we can prove there aren't very many. This is how the assumption of RH gets removed. Okay, I think that's what I want to say, so thank you.
Are there any questions or comments?
So do you know if people are studying or thinking or about longer intervals, so between let's say between t and t plus square root of t or something like that? And what would be the expectation in that case?
Yes, so people are thinking about this to some extent. So there's a paper of Argand, Ouimet, and Radziwill from a few months ago, which looks at the moments of a zeta function in intervals of varying length. And what's going to happen is that so if your interval is like this, things that are distance more than 1 apart are basically independent. And then on intervals of length 1, you have this logarithmic correlation structure. So this would correspond to about h independent tries of the log correlations which are coming up there. So once h is kind of large, even just like a big power of a log would probably suffice. The effect of the logarithmic correlations isn't going to be significant compared with the independence that comes from h. So this is why, except maybe at very, very low order terms, this doesn't have any impact on the conjecture of pharmacologic cues. So they assume in their conjecture that the maximum of zeta on this big range is like having t independent goes. Now, it's not quite right because of this dependence, but the effect of this dependence is so small compared with the scale that you're looking at that it really doesn't affect anything. So there'll be some range of h where you get kind of transitional behavior between completely independent and what you see here, but the range of h will be quite small. Certainly when h is like square root t, you won't see anything.
Will they do something about the speed at which this testing converges to 1?
Let's see. So for the upper bound, you get a rate of convergence like e to the minus twice g of t. For the lower bound, you get something complicated and worse. So not an exponential speed of convergence. In any event, both of the results presumably aren't right because there should be this next order term that you don't see in either of the results.
So why does this contour shift allow us to completely avoid the zeros?
So you want to show that I want to show this is roughly 1 for most t. If I've shifted a little bit off the critical line, then I can truncate this product here to a Dirichlet series that's not too long. That's the crucial thing. That's the way it's used. So then this will be the zeta function times some kind of sum with some coefficients that's not too big. So the sum only goes up to t to the epsilon. And then I can do a mean square computation. Look at the difference in mean square of this product and 1 and show that it's small. So the effect of a shift off the line is to let you truncate the product in a suitable way. Why can you avoid the zeros? Well, you're only interested in average results.
Yeah, very naive question. So wouldn't it make sense to look at the zeta function on the real part of S equal just a number slightly above a half, and sort of to look qualitatively at the image, you're going to get something in the complex plane. Mm-hmm. And let's say try to study qualitatively what happens under the assumption of Riemann hypothesis, how it forces this picture to look like, because it would give a better idea of what's the conspiracy happening that
Okay.
all these zeros are on the, no?
Okay, so yes, it would make sense. Depends on what you mean by a number a little bit bigger than 1/2.
Yeah.
So if you mean something fixed bigger than 1/2, like 0.51, then we actually understand very well what happens on such a line. We understand, so there's this universality phenomenon, we understand the distributional properties of zeta very well. It's because you have this mean square convergence, which I talked about at the very start. If you want to see how the conspiracy unfolds as you approach the 1/2 line, then you can't look at 0.51 or 0.501 or whatever. You have to look at 1/2 plus some function that goes to 0 as a function of t. So it is possible to do that, but what tends to happen is that you can't really get any more than whatever partial results it's possible to get by working on the line directly. So somehow in the proof of this result, The last thing I said here, what do? You move off the line a little bit by some amount that goes to 0 as t tends to infinity. You prove something there, you come back to the 1/2 line. Well, the quality of the result on the 1/2 line is essentially just the result that you got when you were a little bit away from the 1/2 line. So this is often how the proofs go. It doesn't seem to give any more understanding of the behavior.
Other questions? Oh, so I have two. So in the end of the argument, you say that ABBRS exploited the fact that it needed only to prove something for 100% of the values of t. So it suggests that National proves something stronger for all t.
Yes. So I guess you're going to have two different exceptional sets. So you're going to have an exceptional set where it's not true that the zeta function looks like a product over primes. You're going to have an exceptional set of t where the product over primes isn't behaving in the typical fashion. So Najnagel shows that the first exceptional set is empty, I guess, and the second exceptional set, he has the same information as these other people get. So yes, it's a stronger result. It's just stronger in a way that's invisible in the way that it's stated.
So my second question is, in what respect do these theorems depend on the fact that you look at the zeta function and not the L function of a modular form or whatever?
Not very much. So it's just that they don't generalize to other L functions in the most natural way. So what you could do is to look at, let's say, a Dirichlet L function, any fixed one that you want, on the critical line, the behavior would be the same. But this isn't the usual way that you generalize to Dirichlet L functions. What you usually do there is you start averaging over the characters. And there you won't see the same phenomenon. It's important that you have a continuous thing to average over. That's where the logarithmic correlations come from.
There was a surprising sentence in the right way. Just you wrote about the theorems of Sykes and Van Dyck, that there are some limits to what the truth can lie. These are just reading the truth can lie.
Okay.